All right, so on page 7, question 3 says, sketch graphs of functions illustrating each of the following possibilities. One is not possible. So it says we want a function that satisfies the hypotheses and the conclusion of the mean value theorem on some interval 1, 5. So to say it satisfies the hypotheses means the function is supposed to be differentiable. So you're going to draw something that's continuous and smooth, no corners. And if you draw anything between 1 and 5, I'll just pick a point and I'll pick another point. It doesn't matter where you put them. Just draw anything continuous and smooth, then you will have a function that satisfies the hypotheses of the mean value theorem. And by satisfying the hypotheses, it automatically satisfies the conclusion. It's a theorem. So for example, if I were to draw my secant line between the start and end, and then we're looking for a tangent line someplace that's parallel. How many tangent lines are there that are parallel in this picture? There actually are 2, which is totally fine. So there's a tangent line up there, and then maybe one more down there. Satisfies the hypotheses, and then automatically the conclusion. On part B, on the same interval 1, 5, it says we want f to satisfy the hypotheses, but not its conclusion. What do we think about this? I've got a theorem. Says if the function is differentiable, then there's a tangent line that's parallel to the secant line. That theorem is a guarantee. If the function is differentiable, the guarantee is we're going to find some tangent line, maybe even 2 tangent lines, parallel to the secant line. If f satisfies the hypotheses, meaning it's differentiable, the guarantee is in full effect. It must automatically satisfy the conclusion. So this one, it's not possible. There's no way to make something that satisfies the hypotheses of the mean value theorem without automatically satisfying the conclusion. This is more of a logic test than an actual, what does this particular theorem say? The conclusion is there's some tangent line parallel to the secant line. The conclusion was written in real fancy symbols with all this gobbledygook, but we translated that into what it really means in terms of the picture. This is the conclusion. Yeah. Okay, part C. We want something that satisfies the conclusion, but it's not its hypotheses. So we want to make sure that we've got some tangent line that's parallel to the secant line. So again, I'll just pick 2 random points at 1 and 5. And I'll go ahead and draw the secant line. And so in this one, we want it to satisfy the conclusion. So I want there to be some tangent line that's parallel to this thing, but I don't want it to satisfy the hypothesis. I don't want it to be differentiable. So how about we start drawing something? We already buy, even though I haven't finished drawing, that there is a tangent line that's parallel to the red secant line. Yes? So now all I have to do is make it fail the conclusion somewhere else. So how about at this point, we'll make it go up and then jut down. So it's got a corner. You could make it have a jump instead if you prefer. Just make it so you can't take a derivative everywhere. But still, the problem happened after we were able to find something satisfying the conclusion, some tangent line that's parallel. Mm-hmm. Yes, but you can have jumps, so it doesn't have to be a continuous way to connect the 2 points. But yeah, you've got 2 points at 1 and 5, and you can pretty much pick them anywhere. But yes, that's the start and end of the graph. And then the last part here, we want something that satisfies neither the hypotheses nor the conclusion. So we'll draw something with a corner or a jump or something like that. But we also want to make sure that at no point is there a tangent line that's parallel to the secant line. So lots of correct answers to this. So I'm just going to do the same kind of thing I did before. And then I'll draw one example, and then maybe later on you should just practice and try thinking up another example. Could be related, but try to draw something different than we're about to draw. So here's my secant line. I want to make sure I don't have a tangent line that's parallel to that. So how about we draw something that is, let's see, let's draw something that's going up a little bit. Is there a tangent line yet that's parallel to that one there? No. So then I'll just stop it right there, and I'll pick up here, And I'm going to continue from that point down to number 5, and I can do it in any kind of nice way that I want. All of those tangent lines are what? Uphill or downhill? Those are all downhill tangent lines, so certainly none of them will be parallel to the red. So that's an example. It fails the hypotheses. It's not differentiable because of the jump. And it also fails the conclusion. So x to the negative 2. Mm-hmm.
Something that looks like that, except I guess
Okay, so you shifted it to the right so that the vertical was at where's the vertical? 3, something in the middle. Okay, so if you drew that kind of thing, let's see. So if we had, let's just say that 1 is here and 5 is over here. And if 3 is in the middle, then what can you say about the secant line if this is a symmetric kind of thing? Secant line is what kind of a line? Yeah, and it's horizontal, isn't it? If this is a symmetric thing on both sides. So I've got a horizontal secant line. Do you guys think that there are any horizontal tangent lines between 1 and 5 for the curve? No. Tangent lines on the left are all uphill. On the right, they're all downhill. There's none that are exactly horizontal. So that's another example of one that fails both the hypotheses because of the jump, the vertical asymptote, and fails the conclusion. So I think that Nikki's equation might be that. So there are lots of examples of things that that work for each of these different parts, and it's okay to struggle with them. Keep practicing with them, and it will become clearer and clearer the kinds of freedoms that you have as you're drawing the graphs. And I think the more practice you get, the easier it becomes to concoct crazy examples that satisfy all kinds of different conditions. Okay, thank you for the questions. Here's what we'll do. We'll take a quick look at the calendar. Today we're diving into chapter 4, which is the start of all the applications of the derivative. And in today's class, we'll talk about using the first and second derivatives. There's not going to be a whole heck of a lot that's brand new today. We've done a lot of analysis of what the first derivative has to do with the graph of the original function and what the second derivative has to do with the graph of the original function. Today we'll look at those old ideas and maybe put them together in some new ways. Next class on Friday, we have quiz number 6, which is on classes 25, 26, and 27. So the 3 classes including today since the test. All right, so it'll be on the linear approximations. That was the tangent lines. The theorems about differentiable functions. We had 2 that had names, the mean value theorem and the racetrack principle, and then today's stuff. Also, project 6 will be assigned on Friday. You can pick it up early if you wish. Okay, a couple of other announcements. Again, there are a bunch of free workshops here at GCC in January about writing a resume, writing a cover letter, and interviewing. And again, I have the sign-up sheet, so if you have any interest in putting your name on the sheet, you can do that. I will bring this again on Friday, and then after that, I'm going to submit it. You can continue to register for this thing after Friday, but you'll need to call this person or find him in order to get your name on the list. So that's up here. And then the other thing was, I just found out yesterday, but today, right after your physics class, if you're in physics from 12 to 12:50, there is a panel discussion for students, study strategy, AllStars. And so it's a panel of the peer tutors that work here, and they give their best strategies for success. Free pizza, but that's not really supposed to be the draw. It's all the strategies that they will provide. This workshop was run last semester with great reviews. So they're running it again because it was such a success. So I'd encourage you to think about going if you're available. So it's right after, so it's at noon today in the library solarium, 3rd floor of the core. All right, so let's come back here. And we'll jump to, is it on this page? I missed it, right here. Page 9, thank you. Okay, so we'll begin with number 1. Garrett?
In this section, we analyze graphs using derivatives. We've seen much of this before, but now we have derivative shortcuts, power rule, etc. Make calculations that we.
All right, thank you. First, some vocabulary. Here's a picture. You've got kind of a mountain chain graph here, and we have two things up at the top that we're going to call local maximums, or I guess local maxima is the plural. And they're called local maxima because both points are higher than the points that are nearby. And so, sure, this is the highest point on the graph anywhere, but this guy is a maximum of sorts. Even though it's lower than the point on the left there, that point is higher than everybody nearby. Would you guys agree? So if you're walking along this mountain, you have accomplished something. I mean, you've been walking uphill for a while to get to that top point, and you got a pretty nice view. It's not the best view anywhere on the graph, but it's higher than the points nearby. And to say that it's higher than the points nearby is why we use this word local. Locally, it is the highest point, right? Just in that small little range, it's the highest point. If it happens that the point you're focusing on is not only higher than the points nearby, but higher than everybody, then we also call it a global maximum. It's the highest point on the globe, anywhere. Okay, so that point right there is called a global maximum. Here's another synonym for you, an absolute maximum. It is absolutely the highest point anywhere. And then likewise, you have some points down at the bottom. Let's look at this one right here. Is that a local min? Yes, is it a global min? No, it's not the lowest point anywhere. It's low, but it's not the lowest point anywhere. So that point right there, is that the global min? Maybe. Yeah, from what we can see, if this graph were to continue, then all of a sudden that is not a global min, okay? So oftentimes, whether it's a global max or min depends on the domain that you're thinking about. If my domain is just from, say, here over to here, and I stop the graph there, then sure, this one down here is lower than any point out of all the ones that I've looked at, and this one is higher than anything I've looked at. But if we let the graph continue, then where's the global maximum on this graph if it goes forever up and down? There isn't one. So I mean, you could call it infinity, and if the infinity is the thing you're feeling, then you'd say there isn't a global max. There's no highest point. Any point you name, I can find one that's higher. Todd? Not necessarily. For example, if you look at x squared, is there a global max? No, because there's no highest point. Is there a global min? Yes, right there at the origin, even though there's no restrictions on the domain. Let's take a look on the next page. Okay, so number 3, Ernie. Yeah, so coming back to this graph right here, we're going to draw a tangent line at the extrema, the extremes of the graph. So basically the 4 points that we've been focusing on, the local maxes, the local mins. The collection of all the maxes and all the mins is called the extrema, the extremes on both sides. So what kind of a tangent line is there at this point right up here at the top? That's horizontal. And how about at the other local maximum? Also horizontal. How about at the local mins? Horizontal. So nothing new, but just kind of refreshing our memory. Oh, if you're at a max or a min, there's a pretty good chance that you're at a horizontal tangent line. So we don't need to write it because it turns out it's not true, but anyway, that's the conjecture I was hoping we would write. If you're at a local max or a min, tangent line is horizontal. So it's not true because of number 4. Richard? So look at the relative min of this graph. It's that bottommost point. Is the tangent line flat there? No. What can we say about the tangent line at that point? It doesn't exist. It's a corner. That function does not have a derivative at that point. But it's still a minimum, right? I mean, it is a local minimum It's also a global minimum. So we've got a new theorem, actually. If you're at a local min or max, then either the tangent line is flat or the tangent line doesn't exist. Those are the two possibilities. So we'll go to number 5, Abby. For Maz. Okay, so those are our two possibilities. If you are at a local max or min, then the derivative at that point is 0. We saw that in the roller coaster picture, or the derivative doesn't exist, like in this picture right here. Okay, those are the only two possibilities to be at a max or min. Number 6, Josiah. Okay, so just a vocabulary phrase that we will be using over and over and over again. A critical number just means that the derivative at that point is 0 or the derivative isn't defined, doesn't exist. Those two conditions match exactly the ones in Fermat's theorem up above. So all we're saying is that if you are at a local max, then you're at a critical number, because those are the places where the derivative is 0 or not defined. All right, I think question 7 and question 8 is pretty cool, but we're going to skip it for now, and if we have time, we'll come back to it. But let's jump to number 9. Bubba? Okay, so again, critical point means that the derivative is 0 or the derivative does not exist. That's what a critical number is. And you can see I've already started changing the vocabulary that we defined. I'm calling it a critical point here. Okay, so it doesn't make much difference to me, but here's the distinction. Critical number might be x equals 2. A critical point might be, when x is 2, the y value happens to be 7. It's saying the same thing. It's just a matter of, are we talking about only the x coordinate, or are we talking about both points, both parts of the point? So in the first graph in part A, where is a place where the derivative is 0 or does not exist? At the origin. So again, here's the distinction that I don't really care about, but the critical number is x equals what? 0 in this case. And the critical point is when x is 0, what does the y happen to equal? Also happens to be 0. Either way is fine by me if you answer on a quiz. And there are no other critical points on the x squared graph. How about this negative absolute value of x? Are there any places where the derivative is 0? No. Are there any places where the derivative doesn't exist? Yes. And it's right there at x equals 0, or again, the point 0, 0. And then in part C, we have x cubed. Are there any places where the derivative is 0? Yeah. Again, right there at the origin. Any other places where the derivative is horizontal? Or the tangent line is horizontal? Any places where the derivative doesn't exist? No. Okay, so we've analyzed. Turns out the origin is the important thing for each of these 3 graphs. Now let's get our conclusions. We've got a critical point. The question is, do we have a max or min or neither at the critical point? So in part A, that's a min. Now when we say min, normally we're going to be, I'm not always going to write it, but generally we're talking about local. Sometimes you might also happen to be looking at the global. So this one is certainly a local min. It's lower than points nearby. Is it also the global min? Yes, it is. But when we say, if we just say min, we're talking locally. So we could have a bunch of folks that are all mins locally. How about for the next one? What is that point? That's a max, both local and global. And how about in part C? It's neither.
We can erase the vertex formula from our brains.
Absolutely. So the vertex formula you're talking about is what, Garrett? Yeah. Negative b over 2a was a formula that applies to any parabola, right? And you guys have used that formula to figure out where the vertex is. Yeah, and so you don't need that formula anymore. In fact, it's gone, just like that was too easy. So I was planning on doing this Friday, but let's do it real quick right now. You don't need to copy this, but suppose you have a general quadratic function. So it's a parabola somewhere, right? Suppose that we have already forgotten the vertex formula that Garrett has given us. Let's go ahead and take a derivative. Remember, a, b, and c are constants. So when I take the derivative of ax squared, is it a product rule? It's not. The variable is x. That a is a constant. It's a constant multiple. Does it stay or go when I take a derivative? It stays. So then it's really just the derivative of x squared. There's 2x. So I'll write it like that. It's all multiplication, so I can shuffle around. Plus b plus 0. Not going to write that. If I want the vertex of the parabola, that is the turning point, could be a bottom or it could be a top, what's true about the derivative at the turning point of the parabola? It's 0, right? So it makes sense to take this thing and set it equal to 0. And we're trying to solve for x, so let's do it. 2ax equals what? Negative b, and then divide both sides by 2a. Negative b over 2a. And I think that's the right reaction. I mean, it's a theorem that it's possible to prove this without calculus. And you may have seen a proof of this back in 107 in the college algebra class. But the proof involves a very, very ugly completing the square. Like completing the square is normally atrocious, but when you try to do it with A's and B's and C's instead of specific numbers, it gets horrific. So you might have seen this before, but if you did, it was not nearly as simple as it is using the derivative. So I think it's really great. Thank you. Okay, so what's our conclusion? If you are sitting at a critical point, you could be sitting at a min, like in the first picture. You could be sitting at a max, like in the second picture, or you could be sitting at neither. Just because you're at a critical point doesn't mean the function turns there. In this case, the x cubed function looks like it's going to turn. It pauses for just a moment trying to make up its mind, and then says, no, I'm going to keep going. And so it's okay to have a horizontal tangent line, even if the graph doesn't turn at that point. Let's go to number 10, Tiffany. Okay, so I think we just answered that question above, but let's try it here. You can see the horizontal tangent line. So what is that point right there called? That is a critical point. And then there's a critical point over here too, because what's true about the derivative at that spot? It doesn't exist, it's undefined. So two different critical points. In the first picture, is it a max, a min, or neither? It's neither one. In the second picture, is it a max, a min, or neither? Neither. So we want to make sure that we understand Fermat's theorem. It says, if you are sitting at a max or a min, is that what it said? Let's make sure we go back. If you are sitting at a max or min, then you have a derivative that's 0 or undefined, right? If you are at a max or min, then the derivative is 0 or undefined. A lot of people try to read that theorem backwards, and it's just not true. If the derivative is 0 or undefined, then you're automatically at a max or a min. It's not true. We've just seen a couple of pictures where the derivative is 0, but you're not at a max or a min. The derivative is undefined, but you're not at a max or a min, okay? So let's take a look at number 11. We'll go to Lindsay. Okay, so in part A, we've got our friend the parabola. It's been moved a little bit. So that right there is the critical point. I'll draw a horizontal tangent line. And then I'm going to make a little sign test here. This is going to be really informal, but I'm going to drop that point straight down and put it on my number line. And then next to this number line, I'm going to put a little f prime. And the goal here is to think about what's the sign of the derivative at each of these points that are here to the left. So what kind of tangent lines do you get for all of these points out here to the left? They're all downhill negative slopes, right? So no matter where you are to the left of the point, the derivative is negative, because we know that when the function has a downhill slope, the derivative is negative. What kind of tangent lines are to the right of that point? They're all positively sloped. So that right there is a sign test, very informally done, that just says, oh, at the minimum there, the derivative went from negative on the left to positive on the right. Fair enough. Let's take a look at this other one. So again, we're grabbing the critical point. And I'm just going to make one small distinction here. I'm going to put a filled in dot at the critical point that we had before. And I'm going to put an open dot right here. And that's my way of making a note to myself that the derivative at this open circle doesn't exist. Yes? The derivative at that spot doesn't exist. And we use an open circle to indicate that the point isn't really there. So we can get very close to that point, but we can't get there on the derivative. But we can still analyze the signs left and right. So what's true about the signs of all these derivatives here to the left? Those are all negative. And then the derivatives to the right, think of the tangent lines, they're all uphill, positive. And so it's the same exact conclusion as for part A. We were sitting at a minimum, and the derivative went from negative to the left of that point to positive to the right of that point. And it really hardly mattered whether the derivative was 0 at that point or undefined at that point. Still, the sign test looked the same, and the conclusion is the same. Those are both minimums. If we go to this next point, I'll grab the critical number, the critical point up there, bring it straight down to here. I'll fill in my circle. And again, think about the signs of the derivative. To the left, those are positive numbers. To the right, negative numbers. Yeah, that's exactly right. In order for there to be a turning point, there needs to be a change. It needs to be one positive and one negative. And the order in which you see them as you read them left to right completely governs whether you're sitting at a maximum or a minimum. Yeah? In the first picture, we went negative to positive. That was a min. Second picture, same thing. Negative to positive, that's a min. Third picture, it's the opposite. Positive to negative. What kind of a point? That's a max. And then finally, this guy right here, that is a critical point because the tangent line is horizontal. So we'll put F prime for our sign chart. And what's true about the tangent lines here? Those are positive, and the tangent lines here? Also positive. So what Abby was talking about before doesn't apply here because we didn't have a change. We don't have one of each. And what's the conclusion here? We went positive to positive. Was it a max? No. Was it a min? No, it's neither. And that's the indication that it's going to be neither. And the idea here is that, okay, it was easy enough to just look at the pictures and grab this information. But what if you don't have the pictures in front of you? Well, doing this thing with the sign test, if we have the function rule, if I know f of x is x cubed minus 7x, I can do the sign test business. And that's what we're going to spend some time on today. And then I get information about a picture that I don't yet have. So this is supposed to just lead us to this derivative test right here, number 12. So I'll read this one. It says we should be convinced of the following theorem. It's called the first derivative test. We are going to have a second derivative test. I just want to highlight the first derivative test is so named because it deals with the first derivative. Second derivative test, I think it's on the next page, deals with the second derivative. Okay, so that's telling you. I just want to make sure we're clear. It's not called first because we see it first. It's because it has to do with the first derivative. All right, here we go. If f prime of x is less than 0 immediately to the left of some point called x0, and f prime is bigger than 0 immediately to the right, then f has a relative or local, and it's either a max or a min. We just got to figure it out. And for me, I can't handle all the signs. I need to visualize it. If f prime is negative, what is the function doing? It's decreasing. And so in my mind, I say, okay, I've got a function that's decreasing, And then the derivative becomes positive, which makes it increasing. So what kind of a point do we have? Is that a max or a min? That's a min. And so that's our conclusion. I'm just going to write the word local here. I don't think we've used relative yet, but they are interchangeable. Have a relative min. It is lower than all the points, relatively speaking, just nearby. Okay, part B, you can probably guess the answer without reading all the gobbledygook, but if the derivative is positive to the left, what is the function doing? So to the left of the point, the function is increasing, then it hits the point, and then the derivative becomes negative, so we go to decreasing, and what do you have up there? That's some x. And then finally, if f prime has the same sign on both sides, for example, a positive, meaning increasing, and then a positive again, meaning still increasing, then what's going on at that point? Absolutely nothing. Right? Nothing of interest. So if the sign doesn't change, as Abby pointed out, then f has neither a max nor a min. So it's ugly in terms of all the notation. So again, I got to go to the visual. If f goes from increasing to decreasing to decreasing, then what's going on at the point? That's a max. And then on the other side, if f goes from decreasing to increasing, then we have a min. So far, so good? Okay, on the next page, we have one of our crazy symbol things happening. That, what is it? C squared, you bet. That's an x squared. And the function is called g of x. Did that get messed up too? Yeah. Gamma of c. Okay, so here we go. Without any graphing calculator, without any picture to rely on, this is going to be all algebraic. It says use the first derivative test. Well, guess what we're about to do first? Let's find the derivative. So let's find the derivative. F prime of x equals. Three x squared minus 8x minus 16. Yes? Okay. And apparently the points that are important to us are going to be the points where the derivative is either 0 or undefined, right? Those are the two things we're going to do with the derivative. It's going to be almost immediate that we're going to do this with just about every derivative we see in the coming weeks. You're either going to take the derivative and figure out where it's 0 or where it's undefined. Let's deal with the undefined part first. Is this derivative ever undefined? No. So nothing to worry about there, but we would like to take it and make it equal to 0. Now this is a quadratic equation. Quadratic equations are easy to solve. I mean, just use the quadratic formula, or maybe you have a program on your calculator, or you have Wolfram Alpha, you do anything. Like, they're really easy to solve. But I'm going to give you one that's kind of nice in factors. Hardly any of them ever factor, but let's just look at this one, it factors. The 3 makes it awkward, but certainly we can figure out what the first terms are supposed to be. That's the only way to get a 3x squared. It's going to be a 3x and an x. And then I'm looking at 16. What are the possibilities? 4 and 4, 2 and 8, 16 and 1. Okay, so somebody at each table try one of those and we'll pick the one that works. Okay, so we got a couple of people saying 4 and 4, and we got to get the signs right. I guess it should be a minus over there and a plus over there. So you can maybe mentally verify that that works, and I trust that we could all get there, even if it didn't happen to be the first one you tried. If you tried 8 and 2, you would see when you foiled it together, you didn't get what you wanted, so you try a different one. So really, trial and error is fine. And so then we'll take each piece and set it equal to 0. So we go 3x plus 4 is 0, or x minus 4 is 0. So how much is x? Good. Is everybody okay with the 2 places where the derivative is 0. Let's practice our vocabulary. What are these two things called? They are zeros of the derivative. Today we called them critical points, or I guess in this case these are the critical numbers because they're just the x's. But like I said, critical point, critical number, they're just about synonyms for me. So we found our critical numbers. Now what we need to do is figure out what's going on with the first derivative on either side of these critical numbers. So we're going to do something that is going to become very commonplace in this class, and that's doing a sign chart. So you're going to put the two numbers on your number line. The only thing you got to make sure you do is put them in the right order. Small numbers are to the left, big numbers are to the right. So the first number I put, I'm actually not going to put 0. I just want these two. Yeah, so -4/3 goes first. And over here is the number 4. And don't worry at all about the scale. You just got to worry about the order. If you get them in the wrong order, you're going to get crazy results that aren't true. Just for kicks, I'm going to put solid circles in here to distinguish them from points that don't exist. The derivative exists perfectly well at these 2 points. In fact, how much is the derivative at each of those points? It's 0. That's how we found them. So at the moment, we know that the original graph is flat. Imagine x cubes. They oftentimes look like an S on the side. And so how many turning points does a typical cubic graph have? It's got 2. We just got to figure out which one, maybe one's a max and the other's a min, and let's find it. So again, I want to highlight, I'd really like to see that next to that number line to tell me what function you're plugging into. Because at the moment, I have 2 functions up on the board. I've got the original f that I could do a sign chart on, and I've got the f prime that I could do a sign chart on. And on the next page, we'll have an f double prime that we could do a sign chart on. So you really want to be clear and label what it is you're plugging into. Okay, so there's an easy way to do the sign chart, and there's a hard way. Hard way first. Pick a number that is bigger than 4. 5, super. I'm interested in knowing what f prime of 5 is. Yes? I want to plug 5 into the derivative. So I plug 5 in. 3 times 5 squared, 3 times 25 is 75. Minus 8 times 5 is 40. 75 minus 40 is 35. Minus 16, is that 19? Super, 19. That's a lot more work than we need to do. So ultimately the answer is 19, which ultimately means what kind of numbers are out there? Positive. Okay, far better than what I just did is to say, okay, I'm interested in not necessarily knowing that it's 19. I only care whether it's a positive number or a negative number. So how about instead of plugging 5 into the original, let's plug 5 into this guy. If I plug 5 in for this x, don't actually do the calculation, but tell me whether it's a positive number or a negative number. It's definitely positive. If I plug 5 in for this x, 5 minus 4 is a positive number. When you multiply 2 positives, what do you get? You get a positive. So that's way less painful than doing the arithmetic way. And then I'll say even better than that. So 5 is a very natural number. A lot of people would pick 5. When I say pick a number that's bigger than 4, I'm never going to pick 5. Because 5 is so close to 4 that if you make a tiny little arithmetic mistake, like when you plug 5 in, what did you get right there? You get 1. But 1 is really close to being a negative number, right? If you made a tiny arithmetic mistake mentally, you just fell asleep for a second, you might accidentally get -1 or -2, I don't know, something, because it's close. So why are we picking 5, something so close to 4? Let's pick 100. If I plug 100 in for the x, in that red circle thing, it is clearly positive, right? It's overwhelmingly positive. So even if I accidentally take 100 and add 4, which wasn't the right thing to do, I'm still not going to get the wrong sign. So for me, I pick x equals 100, I plug it in, okay, really positive times really positive is really positive. Now let's pick something in between, -4/3 and 4. Any number is fine. 0 is oftentimes the easiest number to plug in. If you plug 0 in for x right here, what kind of a number is that? That's positive. Plug 0 for this x, what is that? That's negative. A positive times a negative is negative. In your mind, pick -100 all the way to the left and plug it into the 2 parentheses, the 2 factors. If you plug -100 for each one, what is each factor? They're both negative. Negative times negative is positive. So this is what we get.
Is there any way you can use this to like solve a cubic? Like taking the derivative and finding where the turning points are. That's a way to help find the answer.
I'm not sure what you mean when you say solving or finding the answer to a cubic. What does that mean?
Like if the thing up top was set equal to 0 and you want to know what x was, is there any way you can use the derivatives to help you get there?
It's a good question. To solve a cubic equation is notoriously hard. We have a quadratic formula. There is a cubic formula that's way uglier than, yeah, it's like a page long. So what I can tell you is this. I can tell you that we got a lot of information about the behavior of that original function right here. To the left, the derivative is positive. So what is that function doing? It's increasing. And in between, it's decreasing. And at the right, it's increasing. So already I've got some sense. Maybe I don't know exactly where the thing is, but I know it's going up, and then it's going down, and then it's going up. And so somehow I could maybe use like that behavior. If I know that it's going up, let's say that I'm at this point and I know it's going up, if I'm already positive, then the 0 is someplace to the left. So if you just happen to be at some point and you want to know, well, should I go left or right? This gives you information. Okay, more concrete than that, more precise than that. There is a root finding method, a root approximating method to solve any old equation equal to 0 called the Newton's method or the Newton-Raphson method. We're not going to cover it this semester. I'm pretty sure it's in the book someplace, but it uses the idea of taking a derivative and honing in on a point, even if you can't find it exactly. So that might be something good to look at outside of class, or we could take it in the math club. Good question. Okay, so let's get our conclusions. Can you guys look back to the first derivative test if you need to, and you're going to write here either max or min, and you're going to write over here either max or min. Okay, what is the first one? First one's a max because we went from positive increasing to negative decreasing. That right there is a max. Second one is a min because we went from decreasing to increasing. And so I don't want to say this is the most exciting problem in the world that you've ever seen, but I do want to say that in any previous class where a cubic equation came up, at some point they said, the teacher would say, okay, graph it on the calculator because we don't have the tools to figure out where anything is, where stuff is happening. And so maybe a cubic that you were given was already in factored form. That was nice of us. X minus 2 times x plus 4 times x minus 3. You can then plot the 3x intercepts by looking at that thing because luckily it's factored. And then you can maybe do a sign chart on this thing and decide whether it was below the x-axis or above. And so maybe you come up with something that says, oh, all right, so at 2, it's equal to 0, and at negative 4, it's equal to 0, and at 3, it's equal to 0, and it's positives out here, and negatives here, and positives here, and negatives here, and then you connect the dots in some way. Okay, it was positive, and then it's got to be negative, and then it's positive again, and it's negative. So the cubic looks like that, and invariably some very curious student would say, okay, but where's this point? And how high is it? And where's that point? And how low is it? And we would say, well, on the calculator, you can use the maximum command and estimate it to a certain amount of accuracy. And it's because we didn't have the ability to say anything concrete about the turning points. The first derivative test tells you everything there is to know about the turning points. So we've got tons of information now about this guy. We know exactly where the max is. We know exactly where the min is. If you actually wanted to find the heights of these points, and I guess I would plug these guys into the original function just to find the y values. You can use your calculator to help you if you want. But that would tell you not only, okay, the maximum point here is at negative 4/3, because that's what we found over there, and you can find the y value by plugging negative 4/3 into the original. Maybe it turns out to be 7. I'm just making something up. So a familiar graph, but with a lot more nuanced understanding of it. Okay, so that is good. Last thing that I'll say about that one is, and this is going to be a little bit of a pain, but I'd like us to write a tiny bit more than we wrote here. We wrote the words max and min. In calculus, we'd like to justify a little bit more precisely than just here's the sign chart and read it and then conclude max and min. So I'm going to write down what I think is the most compact way that I think fully justifies the max and min conclusions. Something like this. Since f prime goes from positive we can abbreviate positive to negative at x equals negative 4/3, comma. What's going on at negative 4/3? It is a critical point, and what kind? It turns out to be a maximum. X equals negative 4/3 is a max. There are other ways to write it. I'm open to other ways of writing it. This is the shortest way that I can share with you to write it, okay? But you just need to convey to me you understand this idea of the derivative to the left and the derivative to the right, and therefore max. Questions on that?
When we're writing it like,
Mm-hmm.
do we have to specify?
Yeah, I assume local unless you say this is the global maximum. Yeah, good question. Okay, so maybe write the other sentence. There's a corresponding sentence for what's going on at x equals 4. Okay, so if we've got our sentence written, let's take a look at part B. Part B is going to work exactly the same as part A. We're going to take a derivative, we're going to find the critical numbers, and we're going to do our sign chart. The only difficulty is that the derivative is going to be messier because we've got a fraction here. And so the analysis will be a little bit tougher, but the calculus part is exactly the same. So let's take our derivative here. Which rule? Got to use a quotient rule. So let's use the quotient rule. What do I write down first? Because I always forget it. Bottom squared. Quotient rule starts top or bottom? Bottom. X minus 1 in parentheses times 2x, derivative of the top. Plus or minus? Minus, copy the top, times derivative of the bottom, just 1. Okay, so that's what we get with the quotient rule. And I will tell you that when we apply this quotient rule with polynomial things like we have here, we're going to want to distribute upstairs. Never distribute downstairs, always distribute upstairs. So we're cleaning this thing up, distributing the 2x through there. So we go 2x squared minus what? 2x, and then minus x squared. Still have the same denominator. No need to ever FOIL downstairs. And then combining like terms, what do we get here? X squared minus 2x over x minus 1 squared. So that's as cleaned up as we can make it, but I will encourage you to do one more algebraic thing before we do the calculus. What made it easy to find these critical numbers was that we took our original derivative and factored it, right? If the thing is factored, then it's easy to find the zeros. So I will encourage you to factor as much as you can whenever you have a derivative. So what can we factor out upstairs? X. So we go x minus 2 over x minus 1 squared. That's as good as we're going to make it. Okay, so now what we're looking for, again, is the critical numbers. Critical numbers come from two sources. Either the derivative needs to be 0 or undefined. Doesn't exist. We've got both of them in this problem. So let's look at the 0 part first. How do we make, so I'm just going to write down here, critical numbers. How do we make a fraction equal to 0? It's make the numerator equal to 0, right? So let's make the top equal to 0. What value of x makes the first part? Okay, so 0 makes the first one. What value of x makes these parentheses 0? 2. Those are two critical numbers that make the derivative 0. How do you make a derivative, how do you make a fraction undefined? Make the bottom equal to 0. What value of x makes the bottom 0? X equals 1. Don't FOIL down there. You're ready, it's factored. X equals 1. Okay, x equals 1 twice, but x equals 1 is the only critical number downstairs. So just pointing out, when you have a derivative that happens to be a fraction, you set the top and the bottom equal to 0 for different reasons. You set the top equal to 0 to make the whole thing, the whole fraction equal to 0. You set the bottom equal to 0 to make the whole thing undefined. Ultimately, you just need to set them both equal to 0, but I like thinking about why. So we've got our critical numbers, and we're going to take these critical numbers and throw them on a sign, throw them on a sign chart. So let's do that now. So you just have to put them in the right order, 0, 1, and 2. And again, I want to make a little point here of filling in open circles and closed circles. What's going on at 0? Is that filled in or is that open? That's filled in because 0 came from making the top equal to 0. How about x equals 1? That's an open circle. At x equals 1, the derivative is undefined. And then at x equals 2, that's filled in because the x equals 2 came from the top, right? So anything where the derivative is undefined, open circles. Okay, so let's give this a shot. We're going to plug, one more thing. I forgot to label my sign chart. F prime is what we're plugging into. G prime, thank you, Todd. G prime is what we're plugging into. And this is the G prime that is the best for us. The fully factored version makes the sign chart easiest. Okay, so we're doing a sign chart. And again, it means pick a number way out here, way bigger than 2, for example, 100. We're going to plug 100 in to here. What kind of a number is that when x is 100? That's positive. What kind of a number is this when x is 100? Positive. What kind of a number is this, including the squared, when x is 100? Positive. So we've got lots of positives. Feel free to put little plus signs everywhere if you can't keep track of all the signs. But ultimately, what's going on out here bigger than 2 is definitely positive. Okay, so now things get a little bit messier because between 1 and 2, there aren't any integers. So we'll just pick 1.5. But I think we can still do this without a calculator. If we plug 1.5 in for x, what kind of a number is that? That's positive 1.5. What kind of a number is this when x is 1.5? That's a negative. Don't get worried about the details. Don't think, oh, it's negative 0.5 and then I have to keep track of that number. You don't. It's negative. And how about the bottom? Positive. In fact, as you plug into the bottom, you might say, well, wait a minute, do I even care about the bottom? Because it's always positive because of that squared. So ultimately, it was a plus, a minus, and a plus. Put them together and get minus. And we go between 0 and 1, for example, 0.5. X is positive 0.5, so this thing is positive. This thing is negative. This thing is always positive, so it was now a plus and a minus and a plus. So over there, it's negative. That breaks our pattern of alternating. A lot of times the pattern is plus, minus, plus. How come this one stopped alternating? It's not just because the thing is downstairs. It's true, there isn't an extrema there, and it is undefined at x equals 1, but neither of those are the reasons why this thing didn't alternate signs. It is vertical, but there's something. And it is going to be the same on both sides of 1. But why? What's going on with that particular function? What's special about x equals 1 that we didn't alternate? It's not because it's undefined. What's going on with the factor that came from this x equals 1? Well, that's the x minus 1. But what's true about the x minus 1 factor? It's squared. Normally, when you go from, say, 1.5 to 0.5, what would happen to the sign of this guy right here? When x is 1.5, what is that? That's a positive. When x is 0.5, what is that? It's a negative. It should have changed, right? As soon as you go from one side of the 0 to the other, the factor changes sign. But this factor happens to be squared. And so we lose the alternating piece. If you buy into all that, then actually doing the sign chart becomes really easy because you just need to do one and then ask yourself, are we alternating sign or are we staying the same? As we cross over 0, why is x equals 0 here? What factor did it come from? It came from this x. Don't worry about top or bottom, but just identify the factor. Doesn't matter where it came from. Is that guy squared? No. Unless you've got an even power on the factor, it changes sign. So I can tell you very concretely, this is going to be a plus. I would not encourage you to do that as like in the first examples of the homework tonight, like just plug numbers in. But as you do it enough times, you start to kind of see the pattern. Why do things almost all the time alternate and occasionally it doesn't? Okay, so can you guys write down conclusions? You got 0, 1, and 2. Your options are max, min, neither. All right, so let's come together and get our conclusions. X equals 0 is a max. Again, I always imagine going up, going down. That's a max up there at the top. X equals 1 is neither, because it's decreasing and then it's decreasing again. X equals 2 is a min. And just one sneaky little thing. Suppose that this had been a plus right here. And we're just focusing on that change of sign. Is that a max or a min or neither now? So it's a negative, then a positive. Decreasing, increasing, it's a minimum down there. Except it's not. Because if you go back to the original function, what's going on at x equals 1? It's undefined, right? And so you gotta take that take the results of that first derivative test with a grain of salt. Yes, it's going to be a max if it goes up and then down, and it's going to be min if it does the opposite. But you got to make sure the point is actually on the graph. If you tell me x equals 1 is a maximum without thinking about, oh, what does that actually mean for the original function, then you've been kind of deceived by that first derivative test. Now, oftentimes you're not going to be deceived because things in the bottom tend to show up as, I want to undo some stuff. Things in the bottom tend to show up as a squared, right? When we use the quotient rule, we square, and so oftentimes you won't run into that problem because it'll be the same sign on either side. But that's not really why this is neither a max nor a min. It's not a max or a min because it's not on the graph at all. Okay, moving on. We go to number 15. I think we're up to Chris.
There's another test that can sometimes be used to analyze the concavity of the relative extreme below.
Okay, so I'm picking the local maxes and mins. Just focus on that one single dot. So the numbers are kind of way too small. I didn't intend for us to read them, but is that a 3 maybe at that bottom? Maybe 5. I don't know. Let's just call it C. That number right there is my C. So what kind of concavity does that parabola have at C? It's concave up. So what's true about the second derivative? Is it a positive or a negative number? That's a positive number. Okay, fair enough. That's old. Old news. F double prime of this C is negative because that function is concave down. F double prime at this C. Now, yeah, so maybe it's a 0. So what's going on to the left of the C? It's concave down, and then to the right, it's concave down. So is it concave? But this doesn't matter what's going on left or right. I'm just trying to get a sense. So does that mean at C, it's also concave down? What's true about F prime at that point? It doesn't exist, right? That function has no derivative at this point because it's a corner. Well, if the first derivative doesn't exist, It doesn't make any sense to even think about calculating a second derivative. So this one does not exist, right? The first derivative is undefined. Nothing even to talk about with the second derivative. It doesn't magically link back into existence. So here's our conclusion. If you're at a critical point and the function is concave up, is it a max or a min? It's a min. If you're at a critical point and the function is concave down, it's a max. If you're at a critical point and the second derivative doesn't exist, we have no information. But the first two parts are the first pieces of the second derivative test. So the second derivative test, you still got to find your critical numbers, which is a big algebra problem. But once you've got those critical numbers, you go ahead and find the second derivative, and you plug your critical number, called x0 in this case, into the second derivative. If the second derivative is positive and you happen to be at a turning point, and again, I always imagine pictures. So second derivative positive to me means concave up. So I think of an upwards parabola. What kind of a point do you have down there? That's a min. And if the second derivative is negative, so now I'm picturing a concave down parabola, what kind of a point is there? That's a max. And if the second derivative is 0, I guess we'll add one other piece here, or it doesn't exist, then this test is inconclusive. Go back and use the first derivative test. This just isn't going to work. The conclusion for part C isn't that the point is neither a max or a min. The conclusion is, I can't tell you anything, all right? So just to be clear, we're not saying it's inconclusive, meaning it's not a max or a min. We're saying this test gives us no information. Go back and use the first derivative test.
So all of this wouldn't really help us if you're looking at like reporting, right?
Yeah. So if you have a quartic to start with, and your first derivative has a degree 1 less, and that's cubic. Cubic equations are hard to solve, as we've talked about. We do have Wolfram alpha that can solve any old cubic equation for us. Your calculator can estimate it by using the 0 command. But you're right, we are focusing on cubics because they lead to quadratics, which we know a lot about.
So if we wanted to, if we assume we can graph it, we just graph it.
Finding places where, okay, so the easy ability that we have to graph functions is a fairly recent development, technologically speaking. But finding places where a function is equal to 0 is several hundred years old, and we could do that to great degrees of accuracy before we had calculators in Wolfram alpha. Okay, so here is the second derivative test in practice. So I will just rewrite the first derivative here. These are the same functions we looked at on the previous page. Can somebody remind me, what were the two critical numbers that we found on this example? So finding those critical numbers you have to do for both tests. So up until this point, both tests look exactly the same. But to decide whether each of those guys is a max or a min or neither, here's where the tests diverge from each other. The first derivative test, you draw a number line and you plug points in that are on either side of these guys into the first derivative and look at increasing and decreasing stuff. The second derivative test says, okay, let's find the second derivative. So finding the second derivative from this purple thing, 6x minus 8. Notice I didn't go to the factored version of the first derivative. It's easier to take a first derivative from this than it is to use a product rule. Okay, do we set it equal to 0? No, not for this. The second derivative test just says, take your critical numbers and plug them in to the second derivative. F double prime of -4/3, F double prime of 4. That's all that I care about. Don't need to factor, don't need to set it equal to 0, don't need to do any algebra. You just need to evaluate. And evaluating functions is easy. All right, so I think it's -16, is that true? And we plug 4 in, is that +16? Which is kind of curious, actually, that the concavity at the at the two turning points were exactly the same number, but opposite. Interesting. But all I care about is concluding whether you have a max or a min at each of these points. No. When you plug negative 4/3 in, this guy becomes -8, and then you subtract another 8. Yeah. Okay, so here's our conclusion. -16 is negative. And if your thing is negative for the second derivative, it means concave down. What kind of a point are you looking at? That's a max. So x equals -4/3 is a max. It's the same thing that we got before, but we avoided that whole sign chart for the first derivative. And 16 is positive. Second derivative positive means concave up, and if you are concave up, you are sitting on a min. Okay, questions on that? All right, so we are out of time in just a few moments, so let me quickly point out some highlights. If you are at a point where the concavity changes, I think we used did we use this phrase point of inflection earlier this semester? Yeah, so just highlighting it's a place where the concavity changes. And so what that means is, for example, on this guy, take a look at the blue second derivative, the 6x minus 8. We could figure out where the concavity is 0, and then do a sign test for the second derivative to see, oh, are you concave up and then concave down, or are you concave down and then concave up? Probably either way, that point in the middle is going to be a point of inflection. So finding points of inflection and finding what I'm going to call intervals of concavity means take the second derivative, figure out where it's 0 or undefined, just like we did before, do a sign chart, just like we did before, and then decide, oh, it's concave down this whole interval and concave up this interval. That's it. Last thing, there is on page 14, there's this long interpreting graphs using calculus thing. It's part 1. There are actually going to be 3 different parts for this, but there are a whole ton of problems. I was disappointed. It went A through X. I was so close to getting to a Z question, but I couldn't concoct more questions about that graph. So it's a long thing to do, but I think it's worth some time. I don't know that you'll have enough time to do this and the homework tonight, but over the coming week or so, see if you can, do as much as you can. There is an answer key, and I'd be happy to answer questions and work with each other on this and everything. But I think it's a really good activity. Hopefully, there's some time that you guys can find to try it.
You really couldn't get to Z?
I couldn't get to Z. I mean, I could have artificially gotten, yeah. Like question Y. What is question Y? I don't know.